Welcome to the SBGrid YouTube channel. Software tutorials by developers, lectures by structural biologists, unique content brought to you by SBGrid.
Hello, everybody. Welcome to the SBGrid webinar series. Just a couple process stuff. So our next webinar is going to be April 14th. Jose Luis Vilas is from the Carrazzo Group in Centro Nacional de Biotecnica is going to be joining us to talk about Scipion. For today's webinar, we have Josh Mitchell from Open Force Field, and he's going to tell us about how that works. If you have questions as we go, then you can feel free to use the Q&A feature, or you can send them to the hosts in the chat. And if you or you can raise your hand as a question comes up, we can unmute you. And with that, I will happily turn it over to Josh. So thank you for joining us, and looking forward to hearing what you have to talk about. So,
hi everyone. My name's Josh. I'm from Open Force Field. We're an industry-funded open source consortium, and we're out there to build better force fields for molecular mechanics, classical force fields. So our mission is that we have an open and collaborative approach to better force fields. All of our infrastructure is automated. We write our infrastructure and deploy it in the open. Everything's open source licenses, typically MIT and equivalent. Even our fittings often happen in the open. If you know what you're doing, you can look up GitHub and find exactly how our fittings are going, and our data generation. And we produce state-of-the-art classical force fields and the software you need to create them and run them. And so today I'll demonstrate how we can use one of our alpha force fields, pre-release force fields, to simulate post-translationally modified proteins. And to work our way up to that, I'll demonstrate a few capabilities. You can run this notebook yourself. There's a link up on the screen, or you can follow that QR code. And we are currently presenting these workshops. We've just done a presentation, and we'll do another at the start of April. So if you look up our website, come find us, and you might want to check those out. So today I'm going to introduce a basic open force field workflow, just so that everyone can see how our infrastructure works, and then that should make it clear how you could extend that. Then we will demonstrate a few extensions to get your juices going on what sort of things you can do. And we'll finish up with a simulation of semaglutide, a prominent post-translationally modified peptide. I'll periodically ask for questions as we go. Does anyone have any questions at this point? Okay.
looks good so far.
No one's yelling at me, so I'm going to turn my video off and get stuck in. Okay, so I've already executed everything in this notebook just because some of the cells take a little while to execute. But fundamentally, here's the workflow for using open force field stuff. We generate a topology, which in this case just consists of a single molecule, which we got from Smiles and generated conformers for automatically. So this molecule is paracetamol, if you don't recognize paracetamol's Smile string. So we compile it into a topology, which is sort of a chemical description of what we want to simulate. Then we parameterize that topology with physical parameters so that we can actually perform a simulation. And if you're not familiar with molecular dynamics, which is the simulation technology we'll use, the idea is that we're approximating all the chemistry and physics in our system with a system of uh, Newtonian forces, and then we just step it through time using a Newtonian integrator. And if you step it through time enough and you take sparse enough samples of that trajectory, then you can sample the underlying distribution of how the system behaves. So the way this works here is we take our topology and we apply a force field to it. So a force field is a mathematical description of all the physical interactions in our model. And this is what we produce. We produce these files here, as well as the software we need to use them. If you've ever done MD before, you might not recognize this OFF XML extension. This is a Smirnov force field, which is a SMERC's native open force field format. The idea here is instead of having atom types, we perform what we call direct chemical perception. We directly assign parameters to chemistry by using SMERCs. And SMERCs are kind of like smile strings, except they do chemical patterns instead of whole molecules. So the idea is instead of assigning every atom to a type and then parameterizing based on that type, we go through every atom and every parameter and we say, does this parameter describe this atom? And if it does, we assign the parameter, and if it doesn't, we go to the next one. So once we've chosen our force field, we apply it to the topology to get an interchange. We call it an interchange because we can generate it in a whole bunch of ways, and then we can export it to a whole bunch of different molecular mechanics engines. So in this case, we're going to minimize the interchange and then export it to OpenMM. But we could also export it to GROMACS or LAMMPS or AMBER. And interchange is sort of the focal point where that all comes together. So if you're familiar with MD, this might be new, but this code might be very familiar because this is just OpenMM. Once we're done with this basic open force field workflow, everything just works in the usual way in OpenMM world. So we have a typical OpenMM system, a typical OpenMM topology, a typical list of OpenMM positions, and we just run an MD simulation in OpenMM the usual way, and then we can visualize that. And we can see this gas simulation of paracetamol wiggling in an infinite void of nothing, which is what we asked for. So what just happened? We took 10 lines of code and came up with a chemical system ready to simulate from scratch. We didn't start with coordinates. We just had a molecular identity and a force field. So I think this is really cool. If you're familiar with existing force field engines, they all do their own thing and have various amounts of setup that you need to get to this point. But we can just use some free and open source software and 10 lines of code that take 5 seconds to execute to do this. Unlike other force field formats, our force field format is both fully explicit. It includes everything you need to compute the potential energy or the forces within the force field file. So it includes things like whether you use PME or not, the cutoffs for the non-bonded force fields, for the non-bonded forces, the functional form of all the maths, which atoms should be constrained. All of that is in the force field file and is described by this name. In other engines, those sort of things are split up over multiple different files, or just expected to be remembered by the user. Everything in this system is based on chemistry. It's designed for chemists. We don't go down to physics. It sort of stays in the chemistry world space, thought space. And this setup step is the same no matter what MD engine you use. All you need to change is the export lines and then obviously use different code to actually run the engines. And since this is all just arbitrary, just normal Python code, you can extend it. So we could get molecules from different places. We could get more than one molecule. We could apply a box. We could calculate a box. We could fill the box in some way other than generating conformers. And we'll demonstrate a few of these things over the course of today's workshop. So I think that's a pretty killer set of features for force fields. We hope that that sort of whets your appetite for some open force field stuff, and we'll demonstrate some more specific uses for that in a moment. Does anyone have any questions at this stage about open force field, our mission, the format, anything like that?
I am not seeing any raised hands, questions in Q&A, or questions in chat. So I think we're all good so far.
Great, thanks, Pete. Okay, so if you're following along, I've just put a convenience function to demonstrate simulations in a cell here. I can quickly show you what it is, but I won't go over it. It's just more or less that OpenMM code, but packaged up so that I don't have to rewrite it over and over again. Okay, so I said that there are a bunch of ways you can imagine extending the example I've got above. The first one I want to show is that instead of manually creating a topology by generating velocity positions for a molecule you already know about, we can generate a topology with an external tool. So in this case, we have a wrapper around PacMol. PacMol generates initial coordinates from chemical mixtures, basically. These coordinates are usually good enough that you can start a simulation if you do enough equilibration. And if you've never seen an MD simulation, I think this is a great demonstration because we're going to do a Micelle self-assembly. So we can see here, this is just ordinary Python code. We create a DLPC molecule, which is a lipid from the SMILE string. We create water from the SMILE string, and then we put them together in a box. We ask for a cubic box. We say what we want the density to be and how many of each molecule we want. And then you can see this cubic box of water and lipid. And in this one, you can see the lipids are sort of distributed throughout the water. So this might be a suspension of lipids in water or an emulsion if you really want to call it that. There's no emulsifier, and we'll see that the lipids come out of emulsion really quickly when we simulate it. So then we go back to, that's the only step we've changed. So we have a new topology, that new chemical description of what we want to simulate. We apply our SAGE force field to it to create an interchange, and then we simulate it. And I've simulated this for 1,000,000 steps, which took about 10 minutes. 1,000,000 steps with a 4 femtosecond time step, that's 4 nanoseconds of simulation. And we can then run that simulation, spoilers, and watch that Micelle self-assemble. So these lipids go from being dispersed throughout the solution to sort of clumping up in the middle. And we can see we now have a couple of micelles, a large one, and then maybe a few smaller droplets. If I try to slowly rotate this to give you an idea, we can see these lipids are made up of fatty tails and hydrophilic heads. We can see those hydrophilic heads around the outside, the fatty tails in the middle. And we just started this with a couple of smile strings and some software. And just with 10 minutes of simulation, they self-assemble into oil droplets within water. I'm not displaying the water here, but it is there. So Micelle self-assembly is like one of those demos that I think is really cool. It really demonstrates what molecular mechanics and molecular dynamics, that it sort of works the way you'd expect it to. Does anyone have any questions about what we've just done?
So we have one question in the chat that I think may have been from the previous section. Oh, we've got more questions in the chat. So yes, we do have questions. So from Yura, since the setup is short, many of the parameters must have some default values. And can you say a little bit about what it's optimized for?
Which parameters? Are we talking force field parameters or simulation parameters or
simulation parameters like time step, temperature, thermostat?
So I've just optimized it for like simple laptop lab bench um, simulations, so standard lab conditions. This one doesn't have any pressure coupling, so it's constant number of particles, constant volume, constant temperature. Temperature set at 298.15 Kelvin. The time step here, we use 4 femtoseconds because, when you're doing self-assembly, you want to get as much time out of it as possible. We're using hydrogen mass repetitioning to get that time step up. And yeah, you can dig more into the simulation settings if you like in the but these are defaults that I've set for the purpose of this notebook, not defaults that are in the actual tools themselves.
Excellent. And that transitions very naturally into the question from Lennon, which is, are there restart files available for extending the simulation that's already been run?
Okay, not in this notebook, but the idea for OpenMM is that everything is sort of, you literally write a Python script to do a simulation. So OpenMM has checkpoint files, they're called, that store the exact state of the simulation. They can be written out to XML, and you can store them, restart your simulation, branch it, whatever you want to do.
Recover from cases where the system you're running on crashes during your simulation?
Yep, absolutely. If you run a million steps, then save a checkpoint file, then run another million steps, you just do that in a loop. That's sort of how you do that in OpenMM.
Could you give us a little bit of background about the computational resources to run this particular notebook? I mean, obviously it's going to vary with system size, but
absolutely, yeah. So this system is tiny. So I like made it 50% bigger and didn't notice any slowdown at all. But I'm running on a AMD RX 7900 XTX, which is sort of a top tier AMD graphics card from like 3 years ago. So it's like a gutsy single GPU machine, but not an outrageous single GPU machine. And so it can do these, 6,000 molecules, like 100 atoms a molecule.
Cool.
Is that right?
And I get, so one.
Sorry, 6,000 waters, 30. Yeah.
One clarification on that, then this tool set does not have an explicit CUDA dependency, it sounds like, so you can run it on AMD GPUs.
Yeah, correct. OpenMM runs on AMD, CUDA. Yeah, so it has ROCm backend, CUDA backend. I'm not sure it has an Intel backend yet, but it might.
That is very impressive, because there is a lot of scientific software that you are locked into particular GPU manufacturers. So it's impressive that this is not.
Yeah, let me just be clear. We use OpenMM because like it's our favorite, but we don't produce OpenMM.
Yeah.
We do the force field side of things. But I'm glad people are excited about OpenMM. I think it's a really good engine too.
Yeah. All right. And I guess one last follow-up question is, so for you just added water and there's nothing in there about, which water you're adding. Is that
Right.
a level of detail that's abstracted away and a end user doesn't have to worry about that, but could if they needed to? Or is this picking defaults that they go with?
Yeah, so Sage has a water model included. I think it's tip 3P. Um, our new so Sage is the OpenFF 2.x line. We call that Sage because we called 1.x Parsley and 3.x will be Rosemary, and then we'll do time. We think we're very funny. Um, so Sage, I've completely lost track of what I was just saying.
Water models,
Right.
which
Sage comes with Sage
that
comes
said,
with
I think you answered my question. So
Yeah,
let's.
Sage comes with tip 3P. Because it's all a Smirnoff force field, you can put later parameters later and they sort of overwrite earlier parameters. So you can request, we have like OPC water and tip 4P and maybe a couple of others um, in OFX XML format. So you can choose a different water model if you want. And we'll use OPC later with Rosemary because it works a bit better.
Great. And there's been one follow-up question from Guadalupe in the chat, which this may be a question for the OpenMM team, but is it possible to do implicit simulations, or is that
Implicit solvent?
implicit solvent? Yeah.
Yes, there's a GBSA model in OpenMM,
Okay.
I think.
And what one more follow-up, which again, this may be an OpenMM. Do you know if the acceleration works on the Apple hardware?
Oh, like on metal? I don't
I also don't know
know
off
for
the top of
sure.
my head. So,
Yeah, I don't know, but I don't think so. I think they might have an OpenCL or Vulkan backend, but I don't think they have. Yeah, there's a CPU engine as well, so you can run it on CPU, if that's fast enough for your needs.
and thanks to the collective wisdom of the chat, there is no metal acceleration, but there is OpenCL. So,
There you go.
and Apple was one of the founding people on OpenCL, so hopefully it is still supported even if they don't talk about it.
Fingers crossed. Okay. I'm gonna move on unless someone stopped
We
me
have
real fast.
one more follow-up question, and then
Okay.
yes. So this is we've been generating lots of good discussion here.
Yeah, I love it.
So has the compatibility of the force fields against different solvent models been benchmarked?
Yeah, so we sort of test them against tip 3P and OPC and tip 4P sort of compulsively. And they usually work best with whichever one you parameterize them with. So tip 3P for Sage, and it will be OPC for Rosemary.
Awesome. And Jeffrey, thank you for the statement in the Q&A. Because that looks more authoritative than what I would have said. So thank you.
Jeff's my boss, so you
Yep.
can take what he says as gospel.
Okay.
Okay. All right. The next thing I want to talk about is we're going to simulate a post-translationally modified protein. It's not the last one we're going to simulate. It might be one you've never heard of. But we're just going to get this out of the way so we can show you some stuff that's going on, and then the later one can be a bit more complicated. So upcoming soon, TM will be Open Force Field 3 Rosemary, and also our next gen PDB loader. PDB files are decidedly last gen, so it might be surprising that we need a next gen loader, but we find that everyone wants to use PDB files. And the problem with our approach, if you can call it a problem, is that you need to actually know exactly what the chemistry is of your molecule. So for instance, if you don't have any hydrogens on your molecule, then like we can't parameterize it. We don't know if that's a double bond or a single bond, you know? So and because our force field is so flexible, we have one force field that can parameterize water, drugs, uh, lipids, proteins, all of this stuff. Pretty much anything with, you know, the organic subset, carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, chomps. Um, we can parameterize. Whether it's right or wrong is a different question, but we can parameterize it. So uh, we need to be able to get chemical information out of a format that was just not really intended to store chemical information. It was intended to store coordinates. But people love PDB. People always want to load PDB files. So we've produced this new PDB loader. And the idea there is that instead of sort of implicitly having some residues that we know how to load, we have an explicit residue library that we provide API points to extend. And then we can match chemistries to that library either quickly through by matching names up or more slowly by taking the connect records from the PDB file and matching them up. And then the other step in that is that rather than making a guess, if we're not sure what you've given us, we will just raise an error. We want you to be simulating what you expect. And we're also soon coming up with OpenFF 3 Rosemary. So Sage, OpenFF 2.x, is a drug-like small molecule force field. So it sort of covers molecules that, you know, petition across membranes and dissolve in blood and not necessarily much else. And so we're extending that to proteins to form the Rosemary simulation. But because the same force field will cover both, it will get post-translational modifications, non-canonical amino acids, etc., basically for free. It'll be able to, we hope and expect, it'll be able to generalize to, you know, peptides with a non-canonical amino acid very naturally. And to sort of further support that, we've come up with a graph neural network, AI-based charge model that produces, if you know the lingo, it produces AM1 BCC like charges, but it does it really quickly. So it can do like a 300 residue protein in 30 seconds rather than using all of your RAM and then crashing after 4 hours and not charging anything. And this Rosemary force field is now in an early alpha. So we're going to demonstrate it here on I've never read this word before in my life, Sulaine-Madelin, which is the first stapled peptide ever to make it into clinical trials. It mimics P53 and causes apoptosis in cancer for cancer chemotherapy. So this is Sulaine-Madelin. You can see that it has a peptide backbone along the edge there, and then it has these two non-canonical amino acids that are sort of stapled together. And what this does is it forms a helix, and then that helix is stabilized by this stapling. So we can the PDB format comes along with the CCD, which is the Chemical Component Dictionary. And so one of our next gen PDB loaders features is that you can directly query this CCD. And so we can see that I happen to know ahead of time that the PDB file we're about to try and load, which has been specially prepared, it's not fresh from the PDB, is prepared with these two residues in the PDB file that are then connected by a connect record. So like I think this hydrogen and this hydrogen drops off and forms a bond. And so our next-gen PDB loader will have this abstraction called leaving atoms. And the idea is that you can connect two separate residues together by dropping some atoms from each of them and replacing them with a bond that has the same order as the bond to the atoms that were dropped. And so by default, if we tell the next generation PDB loader to auto download things, it will just use the whole CCD. And so we can naively try and load the PDB file that I've got, this 8gjs prepared.pdb, without any arguments. And it almost works. If we see, we can read the error, and it looks very complicated, but actually the error is simple. What's happened is this non-canonical residue didn't match because it's missing a hydrogen, because that hydrogen has been taken off to form that linking bond between the two residue side chains. And then as a result, the two neighboring residues couldn't match because they wanted to form a bond to their neighboring residue, but didn't know what that would look like. And then that happened again with the other non-canonical residue. So notice that Pablo does know about these non-canonical residues, but it doesn't know about this cross-link, because these cross-links are just something that PDB authors sometimes put in without really, it doesn't get documented in the CCD. So, like I said, our next-gen PDB loader will have an extensible residue library. So instead of jumping through hoops, we just say, okay, so take the CCD, that's a residue library, and then also permit it to have a cross-link between those two residues. And we say, so the CAT atom in the first residue will bond to the CE atom in the second, and then these atoms will be the leaving atoms. And then it loads in 10 seconds, which is pretty good compared to our current PDB loader. And we can see that this is the prepared system that we've loaded. So this is our therapeutic that I'm not going to remember the name of, bound to one domain of the protein that p53 usually binds to trigger apoptosis. And then it's in a saline solvent, 0.1 molar saline solvent. And then we can apply the Rosemary alpha, which has alpha in the name, so that everyone knows it's an alpha, which means that it might be nonsense. And then, like we described before, we specifically say to use the OPC3 water model with it. And this is because, like we explicitly say here, there's no water in the 3.00 alpha, because we technically haven't decided whether we're going to use OPC3 or something, or fit our own water model or do something else. So we're just leaving that possibility open and requiring that end users specify a water model. So exactly the same process as before. We can see this took 11 seconds. This is when charging happens. So this whole protein got charged with the graph neural network in 11 seconds. That's pretty cool. And then we can simulate it exactly the same as before. So constant NVT, 300-ish kelvins, Langevin, etc. 2 femtosecond time step. And we can watch it wiggle. And I don't have any data to show that this is wiggling correctly, but other MD engines and force fields will struggle to parameterize such a complex system in that amount of time or effort. And we can do it like it's nothing. Okay, any questions about Rosemary or our next gen PDB loader?
So two questions. So I guess so going with the one that's more frequent first. So for PDB files, there are probably similar issues whether the PDB entry is in PDB format or MMSIF format, which the protein data bank is moving to. Is this is this limited to one particular ones of those formats, or is that
So
generalizable enough that it doesn't care if it's MMSIF, even if it's got the same data?
um, it is very true exactly that it doesn't care whether it's PDB or MMSIF. So it actually cares so little whether it's PDB or MMSIF that we do not read fields of MMSIF that disambiguate some stuff from PDB file. So we
Awesome.
can read an MMSIF, but we do it very dumbly. We just read its data as though it was a PDB and then process it in the same way. Um, if people want to use our tools and find that frustrating, we invite them to add to submit error reports. But at the moment, no one's asked us for more functionality there, so we haven't implemented it.
Cool. And one other question is that in some cases, the experimenters who are producing making a model based on either cryo-EM or X-ray will use molecular dynamics guided atomic refinement to try to make their structure better. So this is a combination of molecular dynamics and experimental information for when they're putting together their model before they deposit it. Is it possible to reuse those atomic types here, or is that not necessary? Or
You mean like reuse the atom types that were used in the original fitting of the model to the crystallographic data or something like that?
correct? Yeah.
Um, I would guess that's possible, but at that point you're not using our force field anymore. So
Ah,
I
yes,
don't have any
that is an
any
excellent
comment
point.
on
As
that.
soon as you're switching force fields, you should throw away your old parameterization. Yes.
Yes.
Thank you for that answer. And we have one more follow-up. Is it possible to use this to correct or complete PDB entries that have missing atoms, or is that something where you'd want to use a different tool?
Um, I think it's not that tool at the moment. We're sort of debating internally whether we want to make it that tool. But we're a force field organization. We don't really want to take on the entire like system prep stack. But it's open source, so if someone likes what I've done, like they're welcome to extend it to support that sort of stuff.
Yeah. Thank you. And yeah, there are lots of cases where people hear, "Oh, this is an open extensible force field." Well, let's think about applications immediately rather than, you guys are building it and building the infrastructure it needs. So,
Yeah, well, so our small molecule force field works. It's in papers. Open Free Energy, who gave a talk a couple of weeks ago,
yep,
uh, or last week, they use our force field for their ligands. It's amber compatible. If you want to use the Sage force field to do your small drug-like molecules, it's fully ready right now. It's just when you go past small drug-like molecules that we're a bit experimental.
awesome. Well, thank you. And that has momentarily exhausted the supply of questions. So
All right, I'm encouraged that people are asking so many questions. That's really
I
great. Thanks,
I am
James.
too. And actually, as I said that, one more question came in. And
Fantastic.
so,
Hit me.
how is the performance of the force field to parameterize macrocyclic compounds?
Uh, I guess it depends how macro you're talking, but um, the slowest part is always calculating charges, and charge calculation is easy now. Like if we can do I don't know, what, 3,000 atoms? No, like 30,000 atoms for protein in seconds, we can do macrocyclic, I think.
Seconds on a laptop. Yeah, that's
Yeah.
another question. Are glycans on the roadmap for OpenFF?
Um, uh, they are in our hearts, but I don't think they are in any written down in roadmap just yet.
There's always more interesting things to do than there is time to do them in.
Yeah, lipids and proteins are very near term, and then hopefully nucleic acids and maybe glycans sometime after that.
Yeah, thank you.
Great. Okay. So, um, we're now going to go back to Micelle self-assembly because, like I've just said a couple of times, um, our force field isn't really parameterized for lipids. Like drugs don't look like lipids. But OpenMM has like a really good amber force field just ready to go. It can parameterize it. And it turns out that interchange can import things from OpenMM and then combine them as interchanges and then export them to another engine or the same engine. So this demonstration, we're going to take the topology we used before, split it up into the lipids and everything else. And then we're going to parameterize the lipids using OpenMM with the Amber 14 lipid 17. So the lipid 17 force field. Oh, excuse me. And then we're going to recombine them and simulate them. So you could imagine doing this with like some other molecule that you want to open force field eyes. At the moment, we're doing open force field saline, which I don't think has any particularly interesting parameters, but I just want to demonstrate the point, and we'll use it for a more interesting application in a moment. So this is a bit more involved, but like I've said, this is all comes under the category of this is just Python code, write the Python code that does what you want to do. So we just iterate over the Micelle topology that we created earlier. And then if the molecule is DLPC, we put it in one list. If it's a solvent, we put it in another. Then we construct topologies from those lists and give them back the original box vectors. Then we just parameterize the solvent the old-fashioned way uh, with Sage. And remember, if you had non-solvent molecules in here that Sage was good at, it would cover them too. Then this is new code, but it's OpenMM code, so you might be familiar with it. We apply the lipid 17 force field to the lipid topology. We have to choose our non-bonded cutoff and switch distance and everything like that to be compatible with the existing with the Sage force field, because Sage force field like actually explicitly says what they should be in the XML file, whereas lipid 17 does not. And this sort of works out because Amber uses the same non-bonded parameters world as us. We all sort of engineer our force fields to be compatible with each other. And then this is the real magic, is we can then create a new interchange from that OpenMM system and our OpenFF topology, actually. And the reason we use our OpenFF topology is because it has slightly more chemical information in it than the OpenMM topology. So this lets us sort of achieve that dream of being able to carry your association between atoms and chemistry through your whole simulation. And then we can combine those two interchanges using the interchange.combine operator and then inspect what it looks at. And it doesn't look very special because the difference is the parameters and not the actual simulation. But if we do run the simulation, we can see, I don't know if this is just chance, but the micelle forms a bit faster and it's a bit more convincing of a micelle. So this is simulated in half the time, and I don't know. If you ask me, that looks slightly more spherical, but it could just be that I got lucky on this simulation. I don't really have any reason to think that Sage would do badly at Micelle self-assembly. So um, this sort of just demonstrates what interchange is about. Um, we don't only use it to export our parameterized files into whatever engine you want, we can also use it for a limited few engines. I think just OpenMM at the moment, and Chromax or Amber might be experimental, but OpenMM is fairly experimental as well. It can actually import them and then combine them. And so you can imagine all the different ways that you could construct systems by farming them out to different engines and parameterizing them with force fields that only exist in the specified specific format for that engine, and then bringing them back into interchange. And then maybe you save that interchange to a file, and you can come back to it later to simulate more of it. All of that sort of stuff is enabled by this workflow. Any questions before I go on to the big finale?
We do have a couple questions. So, and I think jumping back slightly, so could you speak to about where nucleic acids like DNA, RNA are on the roadmap, and related to that, metalloproteins?
Okay, metalloproteins are like one of those things that we would love to do, but it's still like science world that has to figure that out. Um, so we have
Gotcha.
a few uh, academic collaborators who are actively working on transition metal parameters. We're really excited about that. We want them to happen as fast as possible. We've developed a whole bunch of infrastructure stuff around virtual sites to support that. Hopefully something magic happens there and it just sort of pops into existence. But at the moment, it's not mature enough that we can put it on the roadmap. Um, and I think nucleic acids is sort of sketched on the list after proteins and lipids. Something there.
You have a thumbs up from Jeffrey Wagner, so it sounds like you are down on the right track with that answer.
Thanks, Jeff.
And another question, so about simulating a protein ligand complex, would you recommend running the entire OpenFF parameterized system, or would you recommend doing a combination of, you know, Charm, Amber, one of the other legacy things, and then with the small molecule with OpenFF, which I think is
Okay.
what you were just talking about that in some more detail for this last cell.
Yeah, absolutely. So, I would not recommend combining Charm with Amber or OpenFF because they use very different non-bonded models. They're not parameterized to be compatible. Charm uses a different charging strategy. So definitely don't combine Charm with uh, OpenFF or Amber parameters. But modern Amber force fields, you can sort of mix and match and choose your favorite. So we actually ported um, Amber FF14SB to Smirnoff, and before we had the Rosemary Alpha, we sort of recommended that for um, folded proteins and peptides. Um, so absolutely, like choose the force field you have the most confidence in. We probably at this point have a lot more confidence in our small molecule force parameters than in our application to proteins. So if you want a like production ready simulation, then yeah, for sure, um, use Amber for your proteins, use Sage for your small molecules. Mix and match as you like. Just don't get Charm involved because
Well,
reviewable two will have a field day.
from the perspective of an end user, guidance saying do not do this, things will not behave the way you expect, is very valuable.
Hope so.
So thank you, and I think that is our momentary pause in questions for the moment.
Okay. All right. So it's the moment you've all been waited for, our grand finale. Um, Semaglutide. So if you haven't heard of semaglutide, it's also called Ozempic or Wegovy. It's a new blockbuster weight loss and anti-diabetic drug um, that works by agonizing the GLP-1 receptor. And like the previous uh, drug, it's a alpha helical peptide that's been post-translationally modified. So in this case, instead of being stapled, it has two non-canonical residues. One is 2-amino isobutyric acid over here, which you can just think of alanine with its alpha hydrogen replaced by another methyl group. So this is used all the time because it makes peptides more helical. It's like super alanine for helicity. Um, so that one Pablo can load without any help, but this one is a bit more complicated. So this one is a lysine. See this lysine here that has been labeled with this big long chain, uh, which sort of helps the drug find the receptor and maybe like embeds in the membrane and helps it stick around as well. So um, so you can see here, there's lysine, there's the big modification. Um, I took the time to learn the full name of this one, but I won't for this one because it's too many syllables. Uh, and so we're just doing the same trick as we did before. I've prepared this 7-KIO, which is semaglutide bound to its receptor. This took a lot of work because it was missing half of that very long chain. And then we just teach our CCD cache that it has this cross-link between lysine and this new residue, which is in the CCD. The whole thing is in the CCD. Uh, but um, but it doesn't know to link up with lysine yet. So we just say, okay, these two need to cross-link. We choose the linking atoms that need to link up. We choose the leaving atoms that have to leave to get it in. And now we should be able to load that whole peptide. There's one more bee in the bonnet here, which is that the GLP-1 receptor is a membrane protein, transmembrane protein. And so we need to load um, the membrane, right? The POPC membrane, which I've prepared. The software I use to prepare this membrane does not use the standard PDB residue and atom names. So we have to come up with some other way of teaching um, teaching our next gen PDB loader about it. Now, I could write a really big complex dictionary that says, okay, there's this smile string, and then this atom means this, excuse me, this atom name. Um, and that would load much faster because it could do name-based matching. But I can also just say, there's also another species that I haven't told you about. It's this, it's got connect records. Can you please figure this out? And that's what this additional definitions is for. When you just want to load a PDB file, you already know the chemistry that's in it, and you just want to say, it's this chemistry, can you just load it for me? Then we use additional definitions and we create these anonymous residue definitions. So this does take a bit longer to load from PDB file because this graph matching happens very slowly and it's experimental and it's not cached yet, etc., etc. But once we've waited for it to load, then this is the first molecule in the topology that came out of that PDB. We just visualize it in 3D. And this is what I described to you earlier, right? This is semaglutide. This is a helical peptide with a very long side chain on one of the residues and a second non-canonical peptide, which looks like an alanine with two methyl groups. So that's semaglutide. We've loaded it, no trouble. And we can visualize it in its context. And so here's a whole bunch of water, saline, POPC membrane, and then the receptor. Ooh, just going to be mad at me. There you go. Make it a bit bigger. So here's our GLP-1 receptor, and then semaglutide here. And if we look really carefully, we can see this long side chain poking out here. The first bit of this side chain was in the crystal structure, but the tail is not resolved in the crystallographic density, so I just made that up. Okay. So we've loaded this big prepared topology. All we need to do now is I've moved the positions so that the origin, the molecule is in the center of the box. That's just to make the visualization easier in a bit later. The simulation will work the same way if you don't do this. And then we do that same procedure that we did for the last therapeutic of taking all the molecules in that combined topology, splitting off the lipids. We do this by Hill formula this time. I'm sure there was a good reason for that. Producing the new two lipids, getting their box vectors right, parameterizing one of them with Rosemary, parameterizing the other one with lipid 17 via OpenMM, and then combining them. And then we can simulate them. And so this is just a very short simulation, but it demonstrates the point that we have a free and open source software and force field stack that can simulate a modern blockbuster post-translationally modified drug, peptide drug, without too much work. Fraction of the work that you would need to specially parameterize charge and simulate a drug like this in other engines. Are there any questions about that?
We do have some questions, although with the some of these may be lagging questions, so to speak. But
No worries.
So could you speak to how the force field can parameterize intrinsically disordered proteins or peptides?
Yeah, so we are fitting the force field to quantum calculations on uh uh like amino acids, short multimers, like oligomers of amino acids. And then we think we will also fit it to, we're doing these experiments as we speak, and we sort of just have to decide the best path. And we've taken a lot of different branching paths. But we think we'll also fit, or pretty sure we'll also fit to quite a lot of NMR data. And so we're including both peptides and folded proteins in that data set. Um, there's so yeah, we're sort of hoping we can do really well on both, but if we can't, then doing well on peptides is probably just as likely as doing well on folded proteins.
And that
We may decide to specialize. We're not sure yet.
that naturally transitions into the next question from which was it is your wolf from Abhishash. Can end users add parameters that aren't in CCD or use parameters from quantum mechanics that they've calculated?
Okay. So we don't use parameters from the CCD. We just use chemicals from the CCD. So we use the CCD
Gotcha.
to identify chemistry. There are no parameters in the CCD as far as I know. You can definitely write your own Smirnov force field. So if you have a force field that you think you could break up in terms of Smirk's patterns to assign the parameters to particular chemistries instead of having an atom type system. That might solve the problem that you currently have of having atom types, but having no way to actually assign those atom types. Then we would absolutely love it if you would publish your force field in Smirnov format. And we have some tools. We have it set up so that you can just publish that on Conda or hopefully pip in the near future, and then people can just install it and they will be able to use your force fields as if we published them. So there's an entry point, a Python entry point that you put your force fields in, and as everyone that the end user has downloaded can use any of those force fields as though it was a OpenFF published force field. So we think the Smirnov format is like a great innovation, and we'd love other people to pick it up. So in that sense, absolutely, you can apply your own parameters.
Reducing the technical overhead to sharing scientific information makes the science stuff so much easier, doesn't it?
Yeah, we think so.
Yeah. And one other question. Could you speak to how sensitive could you speak to how sensitive the input confirmation would actually, I should read this verbatim rather than paraphrasing. My apologies, Luis. How sensitive to the input confirmation would parameterization be for a molecule this large?
The parameterization itself is as of OpenFF 2.3.0 completely independent of the confirmation. So all of our parameters are assigned based on chemistry, like this smirks to parameter to physics pipeline. The only exception to that has been charges. We previously used Amber tools or OpenEyes at the end user's discretion, AN1 BCC charges, and we had a whole system for like regenerating conformers, but it's slow and it's conformer dependent at the end of the day, no matter what you do. Our new graph neural network charge models don't know the conformation of the chemical you're giving them. You just give it like essentially a smile string, and it breaks that into a graph and then charges it without having any idea what the conformation is. So we can now confidently say, as of OpenFF 2.3.0, that our force fields are completely conformation independent.
Excellent. Thank you. All right, it sounds like we have another pause for questions.
Great. That's actually all I had prepared for today. If you enjoyed this workshop and you want to come to another one in a month, feel free to go to, sorry, I haven't prepared this, but I know this by heart. OpenForceField, docs.openforcefield.org/workshops/2026, and you can see our schedule for workshops this year. We're doing a fitting workshop in a month or so, where we're demonstrating our brand new PyTorch-based fitting stack. Download our tools, try our examples, check out docs.openforcefield.org. It's got tons of stuff. Raise an issue, get in touch with us. We'd love to hear from you.
Great. Thank you. And Josh, thank you for presenting. And Jeff, thank you for being here and backing up with the technicals or the authoritative statements on various things. Thanks to everybody for attending. And just to mention, because we had some folks joining in who may have been mixed up with the U.S. daylight savings time shift, not matching up with the rest of the world's daylight time shift, this will be up on the SBGrid YouTube channel once we've processed through the video. So, and yes, so I was managing the applause emoji, so were a bunch of other folks, but yeah. Josh, thank you very much for joining us and presenting, and everybody else, thank you for joining and all of the great questions.
Yeah, thanks everyone. That was great. I enjoyed that.
And actually, as long as we're all doing the thanks, thank you for all the work you guys are putting in with Open Force Field.
We love to do it.
All right. With that, we've run slightly over time, so I guess we should cut it short here. But once again, thanks everybody, and have a good rest of your day.